Have you ever checked a weather app and still gotten soaked? It happens all the time. We have satellites, Doppler radar, and supercomputers running complex atmospheric models. Yet, sometimes the forecast is just wrong. Now imagine you are a farmer in the year 1250. Your life, your family's food, your entire survival depends on the weather. There are no apps. There is no news report. There is only the world around you. What do? You learn to read it. You watch the sky, the animals, the plants, even your own body. You learn the signs. The strange part is, many of those ancient methods passed down through generations were not just superstition. They were based on thousands of hours of observation. And science today is showing us that a lot of them are surprisingly accurate. How can a pine cone know it's going to rain? Why do some people's knees ache before a storm? And what can a simple red sunset really tell you about tomorrow? It's number 17. Why does a red sunset mean good weather? You have probably heard the old saying, red sky at night, sailor's delight. Red sky in the morning, sailor's warning. It sounds like a simple rhyme for children. But for a medieval sailor or farmer, it was a critical piece of meteorological data. It was a forecast they trusted with their lives and livelihoods. They did not know the physics behind it. They just knew through generations of observation that it worked. They saw a fiery red sunset and felt relief. They saw a blood red sunrise and felt a knot of anxiety. They knew what was coming. The science behind this ancient observation is both simple and elegant. It all comes down to two things: the way weather systems generally move and the way sunlight behaves in the atmosphere. In the mid-latitudes, where most of Europe is located, weather patterns typically move from west to east. This is a fundamental driver of our climate, pushed by the jet stream. The sun, of course, sets in the west and rises in the east. This gives you a perfect diagnostic tool. When the sun is setting, its light is traveling from the west through a lot of atmosphere to reach your eyes. Sunlight is made up of a spectrum of colors. Blue light has a short wavelength. It gets scattered easily by air molecules. This is why the sky is blue on a clear day. Red light has a long wavelength. It can travel a more direct path. A red sunset means the air to the west is full of dust and other dry particles. These particles are a signature of a high-pressure system. High-pressure systems mean stable air and good weather. So, when you see that beautiful red sunset, you are seeing sunlight passing through a dry, stable air mass that is heading your way from the west. The sailor's delight is the good weather that will arrive tomorrow, but a red sky in the morning is a different story. The sun is rising in the east. For you to see a red sky, the sunlight has to be passing through those same dust particles. But the high pressure system, the good weather, is now to your east. It has already passed you. What is coming from the west, where the weather comes from? A low pressure system. These systems carry moisture and are associated with storms and rain. The red light from the rising sun is illuminating the advancing edge of this wet, stormy weather. The sailor's warning is a warning of the bad weather that is on its way. This is not a new idea. The Greek philosopher Theophrastus, who was a student of Aristotle, wrote about this very phenomenon in his book on weather signs, around 300 BC. He noted that a red sunset meant fair weather. The Bible also contains a reference in the book of Matthew where Jesus says, when it is evening, you say, it will be fair weather, for the sky is red, and in the morning it will be stormy today, for the sky is red and threatening. This knowledge is ancient. It was confirmed much later by the work of British physicist Lord Rayleigh in the 19th century, whose work on light scattering, now called Rayleigh scattering, provided the scientific explanation for why the sky is blue and why sunsets are red. Modern studies have even confirmed the saying is a reliable predictor for the next 24 hours in many parts of the world. It is a perfect example of ancient observation nailing a complex scientific reality. If a simple color in the sky holds such a precise forecast, what other giant atmospheric signals are we missing every day? Could the specific hue, from pale pink to deep crimson, tell us even more about the air's moisture content or the storm's intensity? And what happens to this rule near the equator, where weather patterns are completely different? Number 16, can cows really tell you when it's going to rain? It is an image straight out of a pastoral painting. A field of cows all lying down, contentedly chewing their cud. A farmer in medieval times might look at this scene and decide to hurry the harvest. The folk wisdom says that when cows lie down, rain is on the way. It sounds like a myth, something passed down without any real basis. But like many old sayings, it is rooted in keen observation of the natural world. Animals are far more tuned in to their environment than we are. They have to be. Their survival depends on it. The primary scientific theory behind this has to do with something we cannot feel very well. Barometric pressure. Air has weight, and that weight or pressure changes constantly. A high pressure system is a heavy, dense column of air pushing down. It usually brings clear skies and calm weather. A low pressure system is a lighter, less dense column of air. It is associated with rising air, cloud formation, and eventually rain or storms. Humans are generally oblivious to these subtle shifts unless they are very dramatic. But many animals are not. Cows, with their large, sensitive bodies and complex digestive systems, are believed to be able to feel this drop in atmospheric pressure. The theory goes that the decrease in pressure makes them feel a little uncomfortable. They might seek the comfort and warmth of the ground. By huddling together and lying down, they can conserve body heat and find a more stable, comfortable position before the cool, damp weather arrives. Some researchers have also suggested that a drop in pressure might affect the gases in their stomachs, causing mild discomfort that makes them want to lie down. Another related factor is that before rain, the air cools and the ground is often still warm. Lying down on the warmer ground could simply be a way for the cows to stay comfortable. They are anticipating the chill that comes with the rain. While there is no single, universally accepted scientific paper that says cows lie down because of X, the anecdotal evidence from farmers for centuries is overwhelming. Many modern farmers and ranchers still use this as a quick, informal guide. They will glance at a field and take note. In 2013, researchers from the University of Arizona and Northwestern University published a study that fitted cows with electronic monitors to track their standing and lying behavior. While their primary goal was to monitor cow health, they found a distinct correlation between the cows standing up for longer periods and higher temperatures. Conversely, the data suggested that they spent more time lying down when the weather was cooler and damper, conditions often preceding rain. It is not definitive proof of prediction, but it shows a clear link between their behavior and weather conditions. They are not psychics. They are simply responding to physical changes in the environment that we, with our insulated homes and cars, have learned to ignore. So, if cows can sense pressure changes that predict rain, what other animals are sending signals we are not reading? Can sheep or horses do the same? And is it just pressure, or are they sensing subtle shifts in humidity or even static electricity in the air before a storm? What else are our livestock trying to tell us? Number 15, why do pine cones open and close? Imagine a medieval person walking through a forest. They might have noticed something curious. The pine cones on the ground were not all the same. Some were wide open, their scales splayed out. Others were shut tight like a woody fist. Over time, they would have seen a pattern. The open cones were common on dry, sunny days. The tightly closed cones appeared on damp days or right before it started to rain. This was not magic. It was a simple, reliable weather indicator, a natural hygrometer hanging from every pine tree. The mechanism is a brilliant piece of natural engineering. A pine cone is made up of many woody scales. The purpose of these scales is to protect the seeds nestled inside. When the weather's dry, the cone opens up to release its seeds, allowing the wind to carry them off to sprout elsewhere. When the weather is wet, the cone closes up to protect the seeds from moisture and prevent them from being released in conditions where they are less likely to travel far or germinate successfully. The way it works is based on the structure of the scales themselves. Each scale is made of two different types of tissue layered together. The outer layer of the scale is more porous and absorbs moisture from the air readily. The inner layer is denser and does not. When the air is humid, the outer layer of each scale absorbs water and swells up. This expansion on the outside forces the scale to curve inwards, causing the entire cone to close. When the air is dry, the outer layer releases its moisture and shrinks. This allows the scale to straighten out, and the cone opens up again. This process is called hygroscopic movement, and it is entirely passive. It requires no energy from the tree. It is a purely physical reaction to the amount of water vapor in the atmosphere. This is so reliable that for centuries, people would bring a pine cone indoors and place it on a windowsill to act as a rustic barometer. If the cone started to close, it was a good sign that you should bring the laundry in. This principle was understood long before the science was. Leonardo da Vinci himself designed a hygrometer in the 15th century, but the pine cone had been doing the same job for millions of years. Modern science has confirmed this mechanism. In a 2012 study published in the Journal of the Royal Society Interface, researchers studied the structure of pinecone scales in detail. They confirmed that the bilayer structure and the different properties of the tissues were responsible for this remarkable opening and closing action. The pine cone is a perfect weather predictor for its own needs. It needs to know the immediate local humidity to decide when to release its seeds. This is exactly the information a person needed in medieval times to predict imminent rain. It is not forecasting a storm 3 days away. It is telling you about the moisture in the air right now, which is often the precursor to rain within the next few hours. If a simple pine cone has such a sophisticated, built-in system for detecting humidity, how many other plants have similar mechanisms we have never bothered to study? Could the curling of a leaf or the closing of a flower petal provide even more nuanced information about the atmosphere? What if an entire forest is a massive, living weather station, and we have forgotten how to read the dials? Number 14, what does a halo around the moon really mean? For people in the Middle Ages, the night sky was not just a source of wonder. It was a clock, a calendar, and a weather forecast. Without city lights, the moon and stars were incredibly bright and clear, and any change in their appearance was noted with great interest. One of the most famous and ominous signs was a halo, a faint ring of light appearing around the moon. An old weather proverb sums it up. Ring around the moon, rain or snow soon. This was not just a superstition. It was an accurate observation of the upper atmosphere. Seeing a halo around the moon means that there are very high, thin, cirrus clouds in the sky. These clouds are typically found at altitudes above 20,000 feet. At that height, the temperature is well below freezing, so the clouds are not made of water droplets. They are made of millions of tiny hexagonal ice crystals. As the light from the moon passes through these ice crystals, it is bent and refracted, much like light passing through a prism. The specific 22-degree angle of refraction of these hexagonal crystals creates the perfectly shaped ring of light that we see as a halo. So, why does this predict rain or snow? Cirrus clouds are often the advance guard of a large weather system. They are the thin, wispy outflows that travel on the upper level winds far ahead of an approaching warm front or a low pressure system. A warm front is the leading edge of a large mass of warm, moist air. As this warm air advances, it slides up and over the cooler, denser air that is already in place. This lifting process causes clouds to form at progressively lower altitudes. First, you get the high, thin cirrus that create the halo. As the front gets closer, these are followed by mid-level clouds like altostratus, which will make the moon look watery or hazy. Finally, the low, thick nimbostratus clouds arrive, bringing the rain or snow. A medieval observer would not have known about ice crystals or warm fronts, but they would have seen the pattern. First, the halo, then over the next 24 to 48 hours, the sky would gradually thicken and lower. And then the precipitation would begin. The halo was the first, most reliable sign that a major change in the weather was on its way. The same phenomenon can happen with the sun, creating a sundog or a solar halo, and it means the same thing. But the lunar halo is often more dramatic and noticeable in the dark sky. This method is still used by amateur meteorologists and outdoors enthusiasts today. It is a very reliable short to medium range forecast. According to a study published in the journal Weather, observations have shown that a lunar halo is followed by rain within 24 to 36 hours about 70% of the time. That is a pretty good track record for a prediction that requires no equipment other than your own eyes. It is a direct visual cue of moisture being drawn into the upper atmosphere, a clear signal that the weather is about to change for the worse. If these high-altitude ice crystals create such a clear signal, are there other, more subtle optical effects in the atmosphere that could give us even more information? Could the brightness or completeness of the halo indicate the size or moisture content of the approaching storm? And why are some halos much more vivid than others? What does that tell us? Number 13, why can you hear things better before it rains? On a still, quiet evening in a medieval village, sounds would carry. The clang of a blacksmith's hammer, the lowing of a cow, the distant peal of church bells. But sometimes those sounds would seem sharper, clearer, and closer than usual. A villager might hear the rumble of a cart from a neighboring town that they normally could not. They would take this as a sign. The air was heavy and rain was coming. They were right. This phenomenon, where distant sounds become clearer, is a genuine indicator of changing weather. The science behind it has to do with how sound waves travel through the air. Normally, during a clear day, the ground is warmed by the sun, and the air near the surface is warmer than the air higher up. The sound waves tend to bend or refract away from warm air and towards cooler air. So, on a typical day, sound waves naturally bend upwards away from the ground. This is why sounds tend to dissipate and do not travel as far. However, before a storm, the weather patterns often change this setup. A layer of warm, moist air associated with the incoming storm can move in at a higher altitude, trapping a layer of cooler, denser air near the ground. This situation is called a temperature inversion. Now, when sound waves travel, they encounter this layer of warmer air above them. Instead of bending up and away into the sky, they are refracted back down towards the ground. This effect essentially creates a channel or duct near the surface, allowing the sound to travel much farther with less dissipation. The distant church bells and rumbling carts suddenly sound like they are right next door. Humidity also plays a role. Moist air is actually less dense than dry air. Water molecules are lighter than nitrogen and oxygen molecules. But more importantly for sound, the increased humidity helps reduce the attenuation of sound waves. The sound travels more efficiently through the damp air, so you have two effects working together. The temperature inversion is bending the sound back down to earth, and the high humidity is helping it travel more efficiently on its journey. People in the past would have learned this through experience. They would notice the strange clarity of sound, and then they would see the clouds roll in. It was a direct audible clue that the structure of the atmosphere above them was changing in a way that precedes rain. This effect is well documented in acoustics and meteorology. For example, during the American Civil War, the sound of the Battle of Gettysburg was reportedly heard over 100 miles away in some directions, but was inaudible just a few miles away in others, a phenomenon attributed to complex atmospheric conditions and temperature inversions known as an acoustic shadow. So, if sound can tell us about temperature layers high above our heads, what other senses are picking up on atmospheric changes? Could changes in smell also be a reliable indicator? And is it possible that the specific pitch or frequency of the sounds that travel farthest could tell us something about the depth and density of the air layers involved? Number 12. Can your aching knees really predict a storm? It is a common complaint often dismissed as an old wives' tale. An elderly person rubs their knee or their hip and declares, "I can feel a storm coming in my bones." For centuries, people have claimed that their old injuries, scars, or arthritic joints can predict a change in the weather. In a medieval world without modern medicine, where almost everyone lived with the lingering aches of hard labor or old injuries, this would have been a common and widely trusted forecast. And as it turns out, there is a good scientific reason for it. The key factor, once again, is barometric pressure. Our bodies are constantly under pressure from the weight of the air around us. At sea level, this pressure is about 14.7 pounds per square inch. We do not feel it because the pressure inside our bodies is pushing outwards with an equal force, creating a state of equilibrium. But when a low pressure system approaches, the external pressure on our bodies decreases. This is where joints come in. A joint, like your knee, is a capsule filled with a lubricating fluid called synovial fluid. This fluid has its own internal pressure. When the external atmospheric pressure drops, the tissues around the joint can expand slightly. This is usually not a problem for a healthy joint, but in a joint that is already inflamed from arthritis or has scar tissue from an old injury, this slight expansion can be enough to irritate the nerve endings and cause pain. The scar tissue is less elastic than normal tissue, and the inflamed arthritic joint is already sensitive. The drop in pressure allows the fluid and tissues inside the joint capsule to swell, putting more pressure on the sensitive nerves. This is not just a theory. Several studies have explored the link between weather and pain. A 2007 study from Tufts University in Boston surveyed 200 patients with knee osteoarthritis. They found a clear connection between changes in barometric pressure and ambient temperature and the severity of the patient's knee pain. Another larger study called Cloudy with a Chance of Pain, conducted by the University of Manchester in the UK, collected data from thousands of smartphone users. Their results published in 2019 showed a significant relationship between pain levels and days with higher humidity, lower pressure, and stronger winds. So, the person with the aching knee is not imagining it. Their body is acting as a human barometer, or more accurately, a baroreceptor. They are sensitive to changes that most of us are not. The pain does not come from the rain or the cold itself. The pain often starts before the bad weather arrives, as the pressure begins to drop. This makes it a true predictive tool. A medieval farmer feeling a twinge in his shoulder would know that the pressure was falling and that it was time to prepare for rain long before the clouds looked threatening. If a drop in air pressure can cause a noticeable physical reaction in our joints, what other more subtle physiological effects are happening in our bodies that we don't even notice? Could these pressure changes affect our mood, our sleep patterns, or even our cognitive function in ways we are just beginning to understand? And could some people be so sensitive that they can feel these changes even without having an old injury? Number 11, why do ditches and ponds smell before it rains? In a medieval village or town, sanitation was not what it is today. Ditches, marshes, and ponds were often filled with decaying organic matter. Most of the time, these smells were a background part of life, but sometimes the odor would become much stronger, rising up from the ground with a distinct, earthy, foul smell. People learned to associate this intensified smell with impending rain. When the ditch and pond offend the nose, then look for rain and stormy blows, as one old saying goes. This was not just their imagination, it was chemistry and physics at work. The science behind this observation is tied to atmospheric pressure and the behavior of gases. The ground, especially in damp, marshy areas, is full of decomposition. Bacteria are constantly breaking down plants and other organic material, producing a variety of gases, most notably methane. These gases get trapped in the soil and dissolved in the water. On a day with high barometric pressure, the heavy column of air pushes down on the ground and the surface of the water. This pressure helps to keep the trapped gases contained. They stay in the soil or remain dissolved. The smell is minimal, but when a low pressure system moves in, the weight of the air decreases. With less pressure pushing down from above, the trapped gases are free to expand and escape from the ground and bubble up from the water. The methane and other fragrant compounds are released into the air and the smell becomes much more noticeable. Humidity, which also increases before rain, plays a part as well. Our sense of smell is more acute in humid air. The water vapor in the air helps to bind with the odor molecules, allowing them to linger and interact more effectively with the olfactory receptors in our noses. So, you have a double effect. The low pressure is releasing more smelly gases from the ground, and the high humidity is making your nose better at detecting them. This phenomenon was a very reliable short-term indicator. The drop in pressure that releases the gases is the same drop in pressure that is causing the clouds to form and the storm to build. It was a direct sensory input telling an observer that the atmospheric conditions were changing in favor of rain. For someone living close to the land, this change in the ambient smell of their surroundings would have been an unmistakable signal. A study on landfill emissions has shown a direct correlation between lower barometric pressure and increased release of methane and other gases, confirming the basic principle on a larger modern scale. If low pressure can release gases from the soil, what is it releasing from plants? Could the smell of rain we sometimes notice on the air be plants releasing volatile compounds in response to pressure changes? And are there other, less obvious smells released from the environment that our brains register subconsciously as a sign of changing weather? What if our sense of smell is a far more powerful weather tool than we realize? Number 10. What can the behavior of smoke tell you? For anyone living in the medieval period, the fire was the heart of the home. It provided heat, light, and a place to cook. And the smoke from that fire was a constant presence. People became intimately familiar with its behavior. They noticed that on some days, the smoke would rise straight up from the chimney in a neat, thin column, disappearing into the sky. On other days, it would seem to get lazy, it would hang low, swirl around, and even curl back down towards the ground. This was a bad sign. It meant rain or snow was on the way. The saying, when smoke descends, good weather ends, is based on sound atmospheric science. The behavior of the smoke is a direct visual indicator of the air pressure and humidity. On a clear, fine day, the weather is dominated by a high-pressure system. This means the air is dense and heavy. As the warm, light smoke leaves the chimney, it rises easily through this dense air, continuing its upward journey in a straight line. However, when a low-pressure system approaches, the air becomes less dense. It is lighter. At the same time the humidity increases, the air becomes saturated with water vapor. This moist air is heavy. The tiny, light particles of soot and ash that make up smoke have trouble rising through this damp, low-pressure air. Furthermore, as the smoke rises and cools, the water vapor in the surrounding air can condense onto the soot particles. This makes them heavier, causing them to stall and even sink back towards the ground. So when a medieval villager saw the smoke from their chimney swirling and descending, they were witnessing a live demonstration of atmospheric physics. They were seeing that the air pressure was low and the humidity was high. These are the two primary ingredients for precipitation. The smoke was essentially drawing them a picture of the invisible conditions above their heads. This was an incredibly useful, localized forecast. It did not tell them about a storm 100 miles away. It told them about the conditions right there, right now, which were ripe for rain. This principle is still understood and used today by people who rely on wood stoves for heat. They know that if they have trouble getting a good draft and the smoke hangs low, it is often a sign of damp, heavy weather. Physicists studying aerosol and particle dispersion model these same effects. The buoyancy of a plume of particles like smoke is directly affected by the density and temperature of the ambient air it is released into. The medieval observation was a perfect practical application of these complex fluid dynamics. If the movement of something as small as smoke particles is so sensitive to atmospheric conditions, what other small-scale movements are we missing? Could the way dust motes dance in a sunbeam or the way pollen drifts on the wind also provide us with detailed weather information? Is the air around us constantly writing messages that we no longer know how to read? Number 9, are birds a better weather forecaster than your app? Animals that fly are deeply connected to the atmosphere. Their lives depend on navigating the currents of the air, and their senses are honed to detect subtle changes. For centuries, people have watched birds to predict the weather. One of the most common pieces of folk wisdom is that when birds fly low to the ground, a storm is coming. Conversely, when they soar high in the sky, the weather will be fine. This is not a myth. The birds are responding to real physical changes in their environment. Like many other animal-based predictions, this one is linked to barometric pressure. When a high-pressure system is in place, bringing fair weather, the air is dense. This dense air provides more lift, making it easier for birds to soar to great heights with less effort. The thermal updrafts that many large birds like hawks and eagles use to gain altitude are also stronger and more reliable in stable high-pressure conditions. So, seeing birds circling high in the sky is a good indication that the air is stable and the weather will remain calm. When a low-pressure system approaches, the air becomes less dense. It offers less lift. Birds have to work harder to stay aloft. It is simply more difficult to fly in than air. This might encourage them to fly lower to the ground. More importantly, the drop in pressure often causes discomfort in the sensitive ears of birds. Like many animals, they can feel the pressure change, and it may be unpleasant for them at high altitudes. Another major factor is their food source. Many birds, such as swallows and martins, feed on flying insects. Insects, too, are affected by changes in the weather. In the cool, damp, low-pressure air that precedes a storm, many insects tend to fly lower to the ground. The birds, being opportunistic hunters, simply follow their food source. So, if you see swallows skimming just above a field or a pond, it is a good sign that both the insects and the birds are responding to atmospheric conditions that point towards rain. A study published in the journal Animal Behavior tracked the movements of a species of warbler using tiny geolocators. The researchers found that the birds would rapidly change their migration altitude to take advantage of favorable winds and to avoid bad weather systems, showing a remarkable ability to sense and react to large-scale atmospheric conditions. While this is about migration, it highlights their sensitivity. The medieval farmer watching the swallows was not seeing a magical act of prophecy. They were seeing a sophisticated biological system reacting to predictable environmental cues. The bird's behavior was a secondary indicator, a signal that the pressure was dropping and the insects were hunkering down. If birds adjust their flight altitude based on air pressure, do they also change their calls or songs? Could the pitch or frequency of birdsong tell us something about the coming weather? And what about nocturnal birds like owls? Are they giving us clues about the weather of the night that we are completely missing? Number 8, why do flowers close up before a storm? A garden in the Middle Ages was not just for beauty. It was a source of food, medicine, and information. An observant gardener would have noticed that some of their flowers seemed to have a mind of their own. On bright, sunny days, they would be wide open. But on other days, even before the clouds gathered, certain flowers would start to close their petals. This was a reliable sign that rain was on its way. Plants like tulips, daisies, and dandelions are all known for this behavior. They were nature's little weather stations. This phenomenon, known as NYCTNST, is the movement of plant parts in response to the daily cycle of light and dark. Many flowers open in the morning and close at night, but some plants also exhibit a similar closing response to other environmental triggers, including a rapid drop in temperature and an increase in humidity. The primary reason for this is protection. Of flowers, pollen, and nectar are its reproductive currency. If they get washed away by rain, the plant's chance of being pollinated is ruined. By closing its petals, the flower creates a protective, waterproof shield for its delicate reproductive organs. The mechanism for this movement is fascinating. It is controlled by a specialized structure at the base of the petal called the pulvinus. This structure contains cells that can rapidly change their internal water pressure, a concept known as turgor pressure. When the plant senses a trigger, like a sudden increase in humidity that often precedes rain, it pumps water out of the cells on one side of the pulvinus. This causes those cells to go limp, while the cells on the other side remain turgid and full. The difference in pressure causes the petal to fold inwards. It is a hydraulic system engineered by evolution. Carl Linnaeus, the famous 18th century botanist, was so intrigued by this that he created a flower clock, or horologium florae. He planted a circular garden with different species of flowers that opened and closed at specific times of the day, allowing him to tell the time just by looking at which flowers were open. He also noted that this clock would be disrupted by overcast or rainy weather, when many of the flowers would remain closed. He observed their sensitivity to atmospheric conditions. For a medieval person, this was a simple and direct piece of information. If the dandelions in the field started closing up in the middle of the day, it was a good bet that you should get your tools out of the field and head for shelter. The plant was not predicting the future. It was reacting to the immediate increase in humidity in the air, a condition that is a direct precursor to rainfall. It was a living hygrometer, just like the pine cone. If some flowers are this sensitive to humidity, could they also be sensitive to other atmospheric components? Can they detect airborne pollutants or changes in atmospheric CO2 levels in ways we could learn to read? And are there desert plants that do the opposite, opening up only when they sense the rare increase in humidity that might signal a coming rain? Number 7, can leeches really be kept in a jar to predict the weather? This is perhaps one of the strangest methods on the list. It involves keeping a leech in a glass jar of water and observing its behavior. A weather glass or storm glass containing a leech was a real device used from the 18th century and likely based on much older observations. The idea was that the leech's activity level could predict the weather. If the leech lay quietly at the bottom of the jar, the weather would be calm and fair. If it became agitated and started swimming around or trying to climb out of the water, a storm was approaching. The most famous proponent of the leech barometer was George Merriweather, a British physician and inventor who showcased his elaborate device, the E Tempus Prognosticator, at the Great Exhibition of 1851 in London. His invention consisted of 12 glass bottles, each containing a leech. When a leech became agitated and tried to climb its bottle, it would trigger a small hammer that would strike a bell. Merriweather claimed that if many bells rang, a large storm was imminent. He was so confident that he lobbied the British government to install his devices at ports around the country. The scientific theory behind this is that leeches are extremely sensitive to their environment. They can detect subtle changes in atmospheric pressure and possibly even electrical charges in the air. When a low-pressure system moves in, the slight decrease in pressure on the water's surface might be detectable by the leech. More compellingly, the buildup of static electricity and electromagnetic disturbances that often precede a thunderstorm could be what is agitating them. Leeches have a very sensitive skin and nervous system, and it is plausible that they can sense environmental changes that are completely imperceptible to humans. While modern science has not definitively proven the exact mechanism, the anecdotal evidence for centuries suggests there is something to it. People who kept these leech barometers swore by them. The behavior seems to be more than random. The leech at the bottom of the jar is in a stable, low-energy state. When it expends the energy to swim frantically or climb, it is reacting to some external stimulus. That stimulus, according to the folklore and observations, is a change in the weather. It is a living, squirming sensor tuned to the invisible forces of the atmosphere. Is the leech responding to pressure, or is it sensing the electromagnetic field of a distant lightning storm? Could different species of leeches be more or less sensitive, and could their specific behaviors, like how high they climb, indicate the intensity of the coming storm? What other aquatic creatures might be even better predictors, living their lives as silent sentinels of atmospheric change? Number 6, what does a mackerel sky mean for sailors? Sailors and fishermen have a rich vocabulary for the sky. They had to. Their lives depended on reading the clouds. One of the most famous and reliable cloud formations is the mackerel sky. This refers to a pattern of mid-level altocumulus clouds that look like the scales on the back of a mackerel fish. The old rhyme captures the forecast perfectly. Mackerel, sky, and mare's tails make tall ships carry low sails. It was a clear warning that high winds and bad weather were on their way. A mackerel sky is formed by high-altitude atmospheric waves or instability. These altocumulus clouds form when a layer of moist air is lifted and cooled. The wavy, scaly pattern indicates that there is a lot of movement and shear in the atmosphere at that level. This is often associated with an advancing cold front. A cold front is the leading edge of a mass of cold, dense air. As it plows into the warmer, lighter air ahead of it, it forces the warm air to rise rapidly. This rapid uplift creates instability and is a powerful mechanism for generating storms. The Mars tails mentioned in the rhyme refer to the thin, wispy cirrus clouds that are often seen alongside the mackerel pattern. These are the same high-altitude ice crystal clouds that create a halo around the moon. Their presence, stretched out by strong upper-level winds, confirms that a large, active weather system is approaching. The combination of the two cloud types was a particularly strong signal. It told an experienced mariner that the weather was not just going to change, but that it was going to change with significant wind and turbulence. They would need to reduce their sail area, carry low sails, to prepare for the coming blow. The English painter John Constable was a master of observing and painting clouds. His detailed cloud studies in the early 19th century were almost scientific in their accuracy. He captured mackerel skies and other formations, understanding that they were not just random shapes, but indicators of the atmosphere's dynamic state. Modern meteorology confirms this ancient observation. The presence of altocumulus undulatus, the scientific name for mackerel sky on a weather chart, is a clear sign to any forecaster of potential instability in approaching frontal systems. The medieval sailor may not have known the term cold front, but he knew what that specific cloud pattern meant for his ship. If the pattern of clouds tells us about wind shear at 15,000 feet, what do the patterns within those patterns tell us? Could the size of the scales or the direction they are oriented provide more precise information about the storm's direction or speed? Are we ignoring a huge amount of data written in the language of the clouds because we are too focused on our computer models? Number 5, why do spiders get so busy before a storm? Spiders are master engineers and their webs are marvels of construction, but they are also vulnerable. A strong wind or a heavy rain can destroy their intricate work in an instant. It makes sense from a survival standpoint for a spider to be able to anticipate bad weather. For centuries, people have observed that spiders have two distinct reactions to an approaching storm. Some will take down their webs and seek shelter. Others, strangely, will work furiously to reinforce their webs, adding extra anchor lines. Both behaviors were seen as a sign of coming rain or wind. The scientific explanation likely lies, once again, in the spider's sensitivity to barometric pressure and humidity. Like many insects and other small creatures, spiders are thought to be able to sense the drop in atmospheric pressure that precedes a storm. This drop in pressure signals a change, and the spider reacts accordingly. Why one spider might take its web down while another reinforces it is a more complex question. It could depend on the species of spider, the location of the web, and the specific atmospheric cues it is receiving. A spider with a web in a very exposed location might decide that the best strategy is to cut its losses and rebuild after the storm. A spider in a more sheltered spot might calculate that reinforcing the web is the better option. Another theory relates to static electricity. The air before a thunderstorm becomes charged with static electricity. Spider silk is a very effective insulator, but it can also pick up a static charge. It is possible that spiders can detect these changes in the electrostatic environment and use it as a cue to prepare for the storm. Their webs, spread out in the air, could act as giant antennas for these atmospheric charges. In the 18th century, the French naturalist and politician Charles d'Orléans de Seignelay was so convinced of spiders' predictive abilities that he kept one as a pet to forecast the weather. He claimed its behavior was a reliable indicator. While this is anecdotal, it speaks to a long tradition of observation. Modern research has also touched on this. A study from the University of Akron found that the properties of spider silk can change significantly with humidity. The silk becomes more flexible and less sticky in very humid air. A spider might be able to sense this change in its own web, realizing that its effectiveness as a trap is decreasing, and that this high humidity is a sign of rain. The act of taking down and often consuming their old web before a storm is also a clever survival strategy. The silk is made of protein, which is metabolically expensive to produce. By eating the old web, the spider conserves those valuable resources, ready to build a new web once the bad weather has passed. It is a perfect example of an animal using an environmental forecast to make an efficient, energy-saving decision. If a spider can sense atmospheric changes with enough accuracy to make a cost-benefit analysis about its web, what does that say about their sensory world? Are they feeling pressure changes through the fine hairs on their legs? And could the specific way a spider reinforces its website, which anchor points it strengthens first, tell us something about the expected wind direction of the coming storm? Number 4, why is dew on the grass a sign of a good day? Early in the morning, a medieval farmer would walk out into his fields. One of the first things he would check is the grass. If it was covered in a heavy layer of dew, he would feel confident that the day would be fair. If the grass was dry, he would be wary. The old saying, "When the dew is on the grass, rain will never come to pass," reflects a simple but accurate piece of meteorology. The presence or absence of dew is a direct result of the atmospheric conditions of the previous night. Real dew forms when the surface of the ground cools down overnight. Under a clear sky, the ground radiates its heat out into space and gets cold. This cold surface then cools the layer of air right next to it. If the air is cooled to its dew point, the temperature at which it can no longer hold all its moisture as vapor, the water will condense out onto the cool surfaces, like blades of grass. For this to happen, you need several conditions. First, you need a clear sky. Clouds act like a blanket, trapping heat and preventing the ground from cooling down sufficiently. Second, you need calm or very light winds. Wind would mix the air up, preventing the layer near the ground from getting cold enough to reach its dew point. These conditions, clear skies and calm winds, are the hallmarks of a high-pressure system. And a high-pressure system means stable, fair weather. So when the farmer saw a heavy dew, he was seeing the direct evidence of a clear, calm night, which is a very strong indicator that the good weather will continue for the next day. But what if the grass is dry in the morning? This means that one of the necessary conditions for dew was not met. It was likely cloudy or windy overnight. Clouds and wind are often associated with an approaching low-pressure system or a weather front. The clouds that prevented the dew from forming could be the leading edge of a rain system. So the absence of dew was a warning sign. It told the farmer that the stable, high-pressure conditions were not in place, and that the weather was more likely to be unsettled. This is a very reliable, short-term forecast. It is not telling you about the weather next week. It is telling you about the weather for the next 12 to 24 hours. The science of straightforward radiative cooling and condensation. The 19th century scientist William Charles Wells conducted extensive experiments on dew and published his findings in his Essay on Dew in 1814. He was one of the first to correctly explain the process, confirming what farmers had known for centuries. If the amount of dew is related to how clear the sky was overnight, could we use precise measurements of dew to calculate the cloudiness of the previous night? And what about frost? Frost is just frozen dew. Does a heavy frost give us an even stronger signal about the stability and dryness of the air mass above us? Number 3, what makes seaweed a weather predictor? For coastal communities in medieval Europe, the sea was everything, and the things that came from the sea, like seaweed, were a part of daily life. People would have noticed that a piece of dried seaweed hung by the door or inside the house would change its texture depending on the weather. On dry, sunny days, it would be brittle and crisp, but when rain was approaching, it would become soft and limp. It was a natural hydrometer, just like a pine cone, but using a different biological material. Seaweed, like many organic materials, is hygroscopic. This means it has the ability to absorb moisture directly from the surrounding air. The cell walls of seaweed contain polysaccharides and salts that readily attract and bind with water molecules. When the humidity in the air is low, the seaweed is dry. But as a weather system approaches, the amount of water vapor in the air too, the humidity increases significantly. The dried seaweed absorbs this moisture from the air, causing it to swell and become pliable and damp to the touch. This was an incredibly simple and effective tool. A fisherman could simply touch the piece of seaweed hanging by his door before deciding whether it was safe to go out to sea. If it was limp and damp, he knew the air was saturated with moisture and rain or fog was likely. If it was dry and brittle, it was a sign of low humidity and fair weather. This method is so effective because it is measuring one of the key ingredients for rainwater vapor. A storm cannot form without moisture in the air. The seaweed provides a direct, tactile measurement of that moisture. This principle of hygroscopy is used in many modern instruments. Some hygrometers use human or animal hair, which also lengthens and shortens in response to humidity. The seaweed is simply a more rustic and readily available version of the same technology. It is a biological sensor that is perfectly tuned to detect changes in atmospheric water content. Could different types of seaweed be more or less sensitive to humidity? Could one type be used for predicting light drizzle, while another, less sensitive type, only becomes damp before a major downpour? And is it just the moisture, or are there salts in the seaweed that also react to changes in atmospheric pressure, making it an even more complex sensor than we realize? Number 2, why do frogs croak more before rain? The sound of frogs croaking is a classic sign of a wet environment, but people living close to ponds and marshes for centuries noticed something more specific. The frogs would often become much louder and more vocal right before it started to rain. A sudden chorus of croaking on a humid evening was a sure sign that a downpour was imminent. This is not because frogs are weather prophets. It is because their biology is perfectly adapted to the conditions that precede rain. Frogs are amphibians. They need to keep their skin moist to survive. They breathe through their skin, and if it dries out, they will die. This means they are most active and comfortable in high humidity environments. The period just before a rainstorm is perfect for them. The air is thick with moisture, so there is no danger of them dehydrating. This makes it the ideal time for them to come out, hunt for insects, and, most importantly, find a mate. The loud croaking you hear is primarily a mating call. The male frogs are trying to attract females. They are taking advantage of the safe, humid conditions to engage in this vital activity. When the weather is dry and the humidity is low, frogs are much less active. They will stay in the water or hide in cool, damp places to conserve moisture. There is little point in expending energy on mating calls when the conditions are dangerous. But when the humidity rises, it is like a green light. The whole population becomes active and the pond erupts in a symphony of croaks. So when a person in the past heard that sudden increase in frog calls, they were hearing the biological response of an entire species to rising humidity. They were not hearing a prediction of rain, but a reaction to the conditions that make rain possible. It was a direct, audible signal from the local ecosystem that the atmosphere was now saturated with water vapor. The rain itself was the next logical step. If frogs are so sensitive to humidity, what about other amphibians like salamanders? Do they have specific behaviors that could tell us even more? And could the specific pitch or pattern of the frog calls change depending on the level of humidity or the drop in barometric pressure, offering a more nuanced forecast to those who know how to listen? Number 1, can the wind's direction tell us everything? Of all the signs in nature, the wind is the most fundamental. It is the engine of weather. In the medieval era, without satellite maps showing pressure systems, the direction of the wind was the single most important piece of information for forecasting. A farmer, a sailor, a miller, they all knew how to read the wind. They knew that a wind from one direction meant one type of weather, and a wind from another meant something completely different. This was not guesswork. It was a system based on the geography and climatology of their specific location. In Western Europe, for example, the prevailing winds are from the west and southwest. These winds blow in from the Atlantic Ocean. They carry moisture, so a steady wind from the west or southwest was a reliable sign of approaching cloudiness and rain. The Old English saying, "When the wind is in the west, the weather is at its best," might seem contradictory, but it often refers to the clearing winds after a storm has passed. A more common belief was that a veering wind, shifting to the west, brought rain. Conversely, a wind from the north or east was a sign of different weather. These winds come from over the large European landmass. This air is typically much drier. An east wind, especially in winter, often brought cold, dry, but clear weather. North wind brought the cold directly from the Arctic regions. So, a simple check of the wind's direction provided a huge amount of information. Is the air coming from a wet source, the ocean or a dry source, the land? Is it coming from a warm source to the south or a cold source to the north? This is the basis of modern meteorology. Forecasters look at the movement of large air masses, a medieval farmer standing in his field, feeling the wind on his face and watching the weather vane on the church steeple, was doing the exact same thing on a local scale. He was determining the origin of the air mass that was currently flowing over him. The 19th century Dutch meteorologist Buys Ballot formulated a law that formally connected wind direction to the center of low and high pressure systems. But the practical application of this knowledge is ancient. People knew that a wind that backs, shifts in a counterclockwise direction was a sign of an approaching low pressure system, and therefore a storm. The wind was the master variable. It told you not just what weather was coming, but from where. It was the story of the atmosphere written in the air itself. All the other signs, the clouds, the animal behaviors, the aching joints, were often just secondary effects, all triggered by the change in the air mass that the wind was bringing in. Reading the wind was the first and most important skill of any ancient weather watcher. We now have complex models to predict the movement of air masses, but are we losing the skill of direct observation? A trained observer standing in one spot be able to feel subtle shifts in wind speed and direction that give a more accurate, localized forecast than a regional computer model. And what other information is the wind carrying in temperature, humidity, and even smell that we have completely forgotten how to interpret?